all. We have an interesting tutorial here this morning, and it deals about TV white spaces, TV white space transceivers. Our presenter is Amr Fahim. His background, he has a Bachelor of Applied Science and a Master of Applied Science with PhD degrees from the University of Waterloo in electrical engineering. He has over 15 years of experience in designing RF and mixed signal ICs for cellular and television consumer products. He's developed innovative solutions to meet the demands of the markets. He's the author of over 25 papers and over 15 patents. He's a reviewer for the IEEE Journal on Solid-State Circuits, the IEEE Transactions in Circuits and Systems, and IEEE Transactions on VLSI journals. So I'll hand over to Fahim.
Thank you, Mr. Chairman. Thank you all for coming this morning. Today we're going to be talking about a very interesting topic that's received a lot of attention throughout academia and industry very recently, and it's actually very active, currently very active in a lot of companies. So it's a very TV white spaces, transceivers is a very large topic. So what I hope to cover today is basically define what TV white spaces are, make sure everybody has an understanding what TV white spaces are, what it's capable of doing, what it's not capable of doing, what problems it solves, and also give you an idea of the design trade-offs involved in TV white space transceivers, and design complexities, giving an appreciation of design complexities in TV white space transceivers. Okay, so this is the outline of my talk. I'll start by first giving an introduction of TV white spaces, like defining what it is and what it does basically, and then I'll go on to TV white space technology overview. So basically, just giving you an idea. Once you define what TV white spaces is, what it does, what problem it addresses, I'll go on and explain basically in a bit more detail, technical detail of what the TV white space technology is, and I'll use an IEEE standard called IEEE 802.22 as a vehicle to explain what TV white spaces is all about. Now, TV white space is actually there are several standards for TV white spaces. 802.22 isn't the only standard, but it's like the US de facto standard. So I'll use that as a vehicle to describe what TV white spaces are, and towards the end I'll talk about all the other standards, just give you a complete picture of what this is all about. And once I go over the standard, I'll go over like a very central topic in TV white spaces, which is the issue of spectral coexistence. TV white space is basically you try to do data transmission on TV channels, on the TV spectrum. So you have to be able to coexist with existing TV channels out there. And I'll go into detail about what this is all about. And in order to be able to do spectral coexistence, you need something called a signal detection spectrum management unit. So I'll go over that as well. So once we've gone over the overview of what technology of what TV white space is all about, I'll go over like an implementation, transceiver implementation of a TV white space enabled device to give you like an appreciation of what kind of specs you try to target, what kind of design complexity or design trade-offs you can encounter. So I'll go over the regulatory constraints, RF requirements, and I'll go over like an example of wideband receiver techniques to support channel coexistence, and I'll go over like wideband transmitters that is required for TV white spaces. Then towards the end, I'll discuss recent deployments here in the US and abroad of TV white spaces, like actual commercial deployments. And then I'll go over, at the very end, I'll go over the non-IEEE 802.22 TV white space standards, just give you a complete picture of what this is all about. Okay, so what is TV white spaces? Well, more generally, really, TV white spaces falls into in a category called cognitive radio. What is cognitive radio? Cognitive radio is it's a device where you can intelligently share the spectrum with other users by dynamically allocating resources. What resources particularly? It's frequency spectrum. Frequency spectrum is in a very high premium. So cognitive radio really started from military applications and by DARPA basically started. And what they were trying to do is basically give the soldier the capability of being able to transmit on an unused channel without being detected by the enemy. So that later on evolved into commercial applications where people started to see, okay, there might be use of this where we have a very limited spectrum, where we can share the spectrum between different users without interfering with one another. So what happened recently is that analog TV ceased to transmit as of 2009 here in the US, for the most part, not completely, but for the most part. And what happened as a result is that people started to say, okay, maybe we can use this extra spectrum for more than just TV transmission, maybe we can use it for data communications. So people started to look into cognitive radio and apply it to the TV, what's called as TV white spaces. And you'll see why it's called TV white spaces, particularly. And the implementation of TV white spaces is the IEEE 802.22 standard. And I'll show towards the end, there's actually several other implementations, not only 802.22. But here in the US, 802.22 is like the de facto standard for TV white space. Okay, so this is basically standard, I guess, frequency spectrum, spectrum usage here in the US. As you can see, it's very congested. Here I'm showing like from all frequencies from near DC all the way up to like several gigahertz. So it's, especially at the lower frequencies, completely congested. So when analog TV started to free up, you had all these little white spaces popping up over here. So that's why it's really called TV white space channels. So this is the TV spectrum usage here in the US. The red components here is basically, here I'm showing the VHF and UHF channels, frequencies rather. So what's marked in red over here is actually not being used by television. It's actually used by other applications such as emergency broadcast or such as like astronomy, radio astronomy, and so on. And the black areas over here is basically the freedom spectrum for analog TV. So once analog TV, these high power towers for analog TV ceased to transmit in 2009, all of a sudden you had all these channels now that became available. Some of them are being reused for digital TV, and others actually are free. Now, all these channels are not completely free, as I noted down here. In 2009, high power analog TV broadcasting ceased in the US, but you still have up till today low power analog TV towers that can still broadcast, and that will remain so up until September 1st, 2015. So what exactly does TV white space address? What this plot shows basically is the data rate versus, it's basically a three-dimensional chart showing the data rate versus the range versus the kind of standard. So here in the central circle is basically the transmission with the lowest ranges. So things like personal area networks or Zigbee, for example, like 802.15 standards that are meant for very low data rates and very local distances, like within tens of meters. Those would fall into the 802.15 standards, and they have transmission distances up to 50 meters. And the data rates can vary from 1 megabit per second all the way up to 10 megabits per second. Then, as you go out a little bit further, you get into the 802.11 standards, which is Wi-Fi standards. And there's different flavors of Wi-Fi. There's 802.A, there's 802.B, N, G, AC, and so on. So there's different flavors of Wi-Fi over here. But generally speaking, the range is limited up to around 33 meters or so. Okay. Then after that, you have another group of standards, again, IEEE standards over here, which are known as metropolitan area networks, and network standards, which is basically the 802.16, which is also known as WiMAX standard. And its range can be extended a bit further. Then finally over here you have something called rural area network, which is the 802.22 standard. And the range of that is typically around 30 kilometers, but can go up to all the way up to 100 kilometers. And if you look at the data rates over here, they're actually quite impressive data rates. And as I'll show later on, this is actually just a data rate for one channel. And there's something called channel bonding in a concept called channel bonding, which I'll go over later on in TV white spaces, where you can have more than one channel concatenate together to give you even higher data rates. So data rates as high as like 400 to 800 megabits per second are actually possible using TV white spaces. Okay, so what exactly? now we have an understanding of, okay, like the type of range that TV white space can address. So it addresses like large ranges, so it's useful for rural area networks. But can we use the spectrum becoming available just for something more than just digital TV? So for example, can we have like a Wi-Fi-like performance for the end users that covers a very large range? So instead of, for example, like how you walk over to like a campus or like to your local Starbucks where you can use Wi-Fi over there, but as soon as you exit, you no longer have Wi-Fi access. So is it possible to have Wi-Fi access over an entire region? And to have like a very high data rates over the entire region. So that's one thing that TV white space can address. Another thing that it can address is can be the last mile wireless link in rural area networks. And namely because it has a wider range than just wireless. The other thing is that it's, and this received a lot of attention very recently, is that it can be an enabler for the Internet of Things applications, IoT applications. So basically you can bridge the gap for remote monitoring control of machine-to-machine devices. And it's expected actually, this is actually a very large, very large market area right now. And it's expected there to be around 50 billion IoT-enabled devices by 2015. Another thing is that the TV white space can be used for, as I said, like examples of these basically can be used for wireless metering, and I'll show more detail what these examples look like. Wireless metering, remote video surveillance can be used for supervisor control and data acquisition, and you can use it also for medical patient monitoring. So how can you use it for these applications? Well, this example over here shows you like an example of how you can set up a TV white space network for wireless metering. So for example, for right now, the way that like standard like 82.15 exists right now, which is basically Zigbee, is that instead of like your person actually physically reading you the values from the metering devices at your home, he could just drive over, and his device would wireless communicates with the Zigbee-enabled device in your home, and get the metering information directly. One step further than that is if you want to apply the TV white spaces, that instead of the truck driver actually driving over, now you have a wireless network, a low-power wireless network, where your metering devices connect directly to a base station, a local base station. And then the base station has some sort of database access over here, where it registers the values from the metering devices to the database. And there's certain companies out there that actually have TV white space enabled, enabled devices that claim their battery life can go up to like 15 years. Another application is remote and supervisor control. So we basically have certain machines over here that have a CPU that are attached to a CPU, and that would be like a TV white space enabled device. We'd get readings out of this device, or over here out of these devices, transmit them to a local TV white space base station, and then would go to like some local database over here that will process the information over, then actually can send control signals back into these devices over here. So the communication can really be like machine to machine, man to machine, or machine to man. Another application is remote surveillance. So you'd have like, you set up TV cameras throughout your home, for example. Then you can, then if let's say you want to know if there's any issues at home, like you can actually see what's happening in your home directly through your TV white space enabled device, and you can get like real-time video transmission. The third application that I talked about, which is remote medical patient monitoring, you have several wearable devices over here. These again would be low-power devices, would be TV-enabled low-power devices that would transmit patient monitoring information to a base station. Again, access to a database, or a doctor can actually access that information directly. Now, as far as the channel, TV white space channel availability is concerned, throughout the U.S., only 5% of the population actually watch over-the-air TV. So that's one issue. That's one point. The other point is that if you look at the usage of the TV channels throughout the U.S., you can see that there's a lot of areas over here that most of the channels are for free. There's only like certain metropolitan areas throughout the U.S. where the number of channels that are available is limited. So that really opens up the possibility of having of using TV white space for rural rural super Wi-Fi. So in rural areas, there's not a lot of TV channels being used. You could just reuse these channels for data transmission and enable very high data rates. And this is a similar map for the UK, like a study was done in the UK. And what's shown over here is basically these two graphs show over here as the same information but under two different conditions. And what is shown basically is that if you limit the amount of power that your TV white space devices can transmit, then you can actually have more data rates available for more channels available for and enabling higher data rates through your TV white space for your TV white space device. Okay, so here just putting everything all together. This is like a heterogeneous 802.22.7. So here you would have like a portable TV white space device, and here you have like a long-range metering device over here attached to your home, and over here you have these fixed devices, TV white space devices for your home or office, and here you have like remote video surveillance device, TV-enabled white space device. So all these can exist in one cell, and yes, you can have actually multiple cells. And the 802.22 protocol actually talks about like what happens when you go from one cell to another and so on. Okay, so what I've done so far is basically just give you an idea of what TV white space is all about, what problems it addresses, what applications it can be applied to, and what kind of ranges we're talking about. Now, one thing that I should mention about ranges is that one feature in TV white space that really does enable it to transmit very, very large ranges is that the TV frequencies, the VHF and VHF frequencies are actually much lower than they are in cellular frequencies. They could go down to the VHF ranges is less than 100 megahertz of a carrier frequency. And it's really that feature that enables that very large transmission distance. Okay, so now I'll go over in more detail of what the 802.22 standard is all about. Then I'll go into spectral coexistence techniques, and then I'll go into the signal detection and management unit. Okay, so here I'm showing an example basically of what the basic components of a TV white space devices are. So there's two main components. There's a base station, and there is something called customer premise equipment, CPE. Okay? So the base station, this is like as any normal transceiver, wireless transceiver, you have a transmitter, receiver here as well. But now you have this new device over here, a new unit over here, which is called a spectrum management / spectrum sensing unit, which is really a distinguishing feature of TV white space enabled devices. Okay. So here, I'm not going to go over like every single little detail of the 802.22 standards, but I'm just going to give you like a flavor of what it's about. It's an OFDM type of area interface, so similar to a DVB-T if you're familiar with DVB-T, or similar to UVLTE. It uses different cyclic prefixes of 1/4 all the way up to 1/32. Again, similar to LTE. It has no MIMO support, which is actually important because, as I said before, the carrier frequencies, which can go down to the VHF range, which is less than 100 megahertz, can be quite low, which would mandate a very large antenna. So if you're to provide MIMO support, you need multiple antennas, which would be difficult to implement. So there's no MIMO support actually in 802.22. The band is supported range from 6 megahertz to 8 megahertz. 6 megahertz is actually the TV signal, the bandwidth of the TV signal, analog TV signal as it is in the US today. And 8 megahertz is like a DVB-T signal. And there's different formats here of downstream and upstream. I'm not going to go into detail of those, but I guess the main point over here is basically that there's been some optimization done in how you allocate the data across all the symbols to try to reduce the maximum phase shift in output power. So they've actually tried to think ahead and basically try to improve the linearity of that power amplifier on the transmitter. The modulation formats can be QPSK, 16 QAM, 64 QAM, and BPSK, again similar to LTE. And also the code rate is actually quite similar to LTE as well. The one feature that TVWS has compared to LTE is that it can actually have an adaptive type of modulation format and coding rate. So it can automatically shift between QPSK and 64 QAM depending on the channel itself. The bit interleaving is done after coding, which is different from like other 802 standards. For example, Wi-Fi, they do it before coding, but that's just a small detail. And here I've just shown the signal frame formats. And this is just for reference. I'm not going to go into detail of everything here, but this is basically the signal frame format of 802.22. There's a super frame, and a super frame is 160 milliseconds long, and it's broken up to 16 frames of 10 milliseconds each. And the interesting thing is that the first frame would have a super frame preamble, but all the other frames have just a frame preamble just to maximize the bandwidth, I guess. Okay, so basically, like in terms of the specs or the standards of 802.22, it's similar to that of it's kind of somewhere between the other 802 standards, IEEE 802 standards, and LTE standards. So somewhere in between those two. Now, with the issue of coexistence is basically the key issue in TVWS. So the main thing is like, how do you reuse the spectrum while not disturbing other transmissions? So, for example, if you have nearby TV transmissions, how can you enable the TV white space device to automatically detect, yes, there is a TV signal there, to avoid transmitting at that frequency and transmit at another frequency that's free. So that's really the key issue in TVWS, a key issue of a coexistence of TVWS. And there's three different methods that are used for coexistence. There's non-cooperative, which is basically first come, first serve. And there's rule-based techniques and there's message-based techniques. So non-cooperative methods, I'll go over right now. It's basically every TPWS-enabled device would try to maximize its own bandwidth on the expense of the whole network. So as you might have guessed, this is really not supported by 802.22, but it's basically the most primitive and basic method. The second method is basically something called rule-based techniques. So you have the base station. Like each network tells the base station where it is, and that's, it requires some data access. Then the base station, depending on certain rules or certain depending on like a database of information has available channels, it allocates the frequencies and the transmission power levels, or dictates the frequencies and output transmission levels to each TVWS enabled device. And I guess the most elaborate one is called the message-based techniques, where you have basically like a two-way communication between the TVWS devices and the base stations. So the TVWS device says, okay, like I'd like some sort of bandwidth, and the base station, and the base station gets it first for all the TVWS devices. Then it tells each TVWS device you can get this bandwidth. But whenever this is done, then you can use his bandwidth as well. So there's some cooperation between the different TVWS devices, but it's done through the base station itself. Okay. Now the issue of signal detection and spectrum sensing. So far we've just said that the main issue in coexistence is that you do not want the TVWS device to transmit on a channel where there is actually TV transmission. The question is, how can we tell whether there's a TV transmission done or not? Well, this is done through something called the signal detection spectrum sensing unit. And this unit, what it does, you must be able to scan the entire spectrum to get an idea what channels are used, what channels are not used. but you also must be able to scan the channel that you're transmitting on. So you transmit for some time, then you stop the transmission. This is called blocking method. You stop the transmission, sense the frequency spectrum out there, then you go back and you then you tell the base station, yes, I detected TV signal, or I did not detect the TV signal. And then the base station then decides blocking methods. The reason why they're called blocking methods is that you actually have to physically stop this transmission, do the sense operation, then you can continue transmitting again. Okay, and these are just some specs for the 82.22. The minimum window, minimum detection window is 30 seconds. So basically, if there's no signal present within 30 seconds, then you can start transmitting. Then after transmitting, it must perform that operation every minute, basically. So every minute you have to keep on checking for that for the channel, whether there's a signal there or not. And you must be able to detect the signal within 2 seconds. The reason for that is that there's a spec within the 82.22 standard that says that you have to cease transmission once the signal's been detected within 2 seconds. So once there's a TV signal, you have to cease transmission within 2 seconds. So the issue of stopping and sending transmission gives about like two metrics that become relevant in the issue of TVWS. The first one is throughput. The second one is latency. So throughput basically is just a measure of the total the data transmission time compared to the total transmission time. So here I'm showing like this data transmission time and some sort of sensing operation done over here. So it's basically the throughput is basically the data transmission time compared to the total time over here. And then latency is basically the maximum duration of a sense time. Okay. So the throughput, like we can't do much about it except try and make the sense operation faster. But latency, we can actually what we can do is we can break up the sense operation to several smaller sense operations to increase the throughput. So for example, like, let's say you need 500 milliseconds of something called quiet time. Quiet time is basically the amount of time you have to stop transmission and actually perform the detection operation. So you need 500 milliseconds of quiet time. So that gives you throughput, I should say here, throughput degradation, not throughput, but throughput degradation of 0.5%, but the latency is around 500 milliseconds, right? So if you break up the quiet time to 50 sections, so instead of being one large section of 500 milliseconds, break it up to 50 sections, your throughput degradation is still 0.5%, but your latency now is much smaller. Instead of being 500 milliseconds, it's now 10 milliseconds. And this technique is actually used quite often in implementations in TVWs. Not only that, but they have something called like fast sensing operation as opposed to accurate sensing, operation. Now, in fast sensing operations, what you do is you try to detect whether there's a large TV signal or not. So that you can do pretty fast, actually. And if no signal is present, then you have to go into the accurate sensing operation just to make sure that there's absolutely nothing there. But if a large signal is detected, you can detect it very quickly, and you can actually stop transmission, go on to a different channel very quickly. And that should increase your throughput. Okay. So there's two metrics here, basically throughput and latency. And you can improve latency by breaking up the sensing operation into smaller chunks. Okay. So this technique was basically relied on something called blocking methods. There's another group of techniques called non-blocking methods, and this is one example of them, which is called frequency hopping. So in frequency hopping, what you do is you have your hardware basically has to consist of a transmitter and actually 2 receivers. So one receiver would be like regular receiver, and the other one would be like a dedicated for sensing the spectrum. Okay, so you have to have like a dedicated spectrum sensing unit. So the way that this would work is that you transmit and receive on channel A normally, and while you're transmitting and receiving on channel A, you'll be sensing channel B. Okay, and 2 seconds later, if there's nothing present on channel B, or whether there's nothing present or not, rather, you send that information over to the base station. Then the base station that it senses that there's nothing on channel B. The base station tells the CPE, customer premise equipment, that yes, now you can start transmitting channel B. So every 2 seconds you change frequencies. The advantage of this is that you do not need to stop your data transmission anytime. You all you need to do is basically just change frequencies. And changing frequencies on wireless transceivers is really mainly limited by the PLL lock time, phase lock time, and these days you can get it down to like within hundreds of microseconds. So that operation is actually reasonably fast. So the way that this works again is that you have transmit and receive a channel A, sends a channel B, then if nothing's there, then you transmit a channel B, and while transmit and receive a channel B, and while you're doing that, they go on to another channel, which is channel C, and you sense that, and you continue this operation with and you keep on alternating every 2 seconds. And this is called frequency hopping technique. And this is just another illustration of this. So you're transmitting channel A, then you go on to channel B, channel C, and so on. Now, so far we've just been saying that we need to detect that signal, but the question is, how do you detect that signal? There's several methods of detection. There's the normal method of detection, which is energy-based detection. So you know you have a channel of 6 megahertz of bandwidth. Then you try to measure the amount of energy within that spectrum, within that bandwidth. The problem with this technique is that, as I'll show later on, the signals that we're trying to measure, TV signal we're trying to measure, actually have an SNR of negative SNR on a dB scale. So you need firstly, you need more than one sample to be able to average out the noise to get to negative SNRs. Secondly, energy-based techniques don't work too well with negative SNRs. The second technique is called feature-based techniques. The second group of techniques, rather, are called feature-based techniques, which utilize the features of existing TV and wireless microphone signals to be able to detect their presence. So what you try to do is try to find like distinguishing features in the TV signal to try to sense whether there's a TV signal there or not. So here I'm showing an illustration of how a TV signal looks like. Here, this is both an analog TV signal and a digital TV signal. Okay. Sorry, this is an analog TV signal and a digital TV signal over here. So the distinguishing feature of an ATSC, which is a digital TV signal over here, is that 7% of the energy is concentrated on the pilot carrier, which is 310 kilohertz offset from the left-hand side of the band. So what your TVWS device would have to do is basically run an FFT on the input on the sensed channel, and then determine whether 7% of the energy of that FFT was exactly at 310 kilohertz offset. Okay. For an analog TV signal, which is an NTSC signal, you have a luminance carrier, which is also called a picture carrier, which is around 1.25 megahertz offset from the left edge of the band. Again, both of these bands are 6 megahertz bands. So for an analog signal, it's 1.25 megahertz offset. So again, you'd run an FFT on your signal, then you'd be searching for a carrier that's a 1.25 megahertz offset from the left-hand side of the band. And if you do sense something there, then that's most likely a TV signal, an analog TV signal. Okay. Now, just to give you an appreciation of how difficult this is, there's different thresholds that you have to use to determine whether there's actually a signal there or not, and then you can adjust the threshold again. Where you adjust the threshold gives you different levels of performance. And this is like a recent study that's been done on recent TVWS enabled devices. So different manufacturers, they have different devices. And this is the detection rate of an ATSC signal, which is a digital TV signal, and an NTSC signal, which is an analog signal, and the false alarm rate. So false alarm means that there was no TV transmission there, and for some reason the device thought there was a TV signal there. So this example shows you that there's still a lot of room for research and development in the area of signal detection and spectrum sensing. And for this reason, actually, if you look at the 82.22 standard, you'll see that there's actually two groups of. It talks about actually three groups of devices: fixed devices, portable devices, but then there's two groups of portable devices. There's portable devices that determine whether they can transmit on a certain frequency or not by looking up by having like a lookup table, and just based on the location, the lookup table will say, okay, for this geographical location, such and such channels are free, you can transmit on those frequencies. So there's those group of devices, and there's another group of devices which are called sensing devices. So sensing devices rely on a signal detection type of techniques, not only on a database, not only on a database. And so these devices are still not considered to be as robust. And as you'll see later on is that the first implementation of TVWS devices actually rely mainly on database techniques to try to determine what frequencies they can actually transmit. And just for sake of completeness, currently there's a lot of research into looking in using second-order statistics of the signal in order to determine whether there's a TV signal there or not. And this is just one recent example. There's actually several examples of this. But right now, this is like a very, very hot research area, basically, to try to determine whether there's a signal there, like signal detection by looking at the second-order statistics of the signal itself, as opposed to really looking at the signal itself. So just to put everything all together, this is like just one example of how a spectrum sensing receiver would look like. You have the antenna, LNA, and there's implied downlinks over here. You go into data converter, INQ data converters, and that will go into an endpoint FFT to try to perform an FFT operation. Then you get the power spectral density over here. Now, the reason why you need the scaling over here is actually very important. Which the reason for needing this is that when you're actually doing the sensing operation, you actually do it over on the same channel, but you do actually multiple runs on the same channel. So as you're doing the multiple runs on the same channel, you can get channel fading, which means that your incoming signal amplitude can vary over frequency. Vary over time. Which means that your RSSI here will be changing the amplitude, will be changing the gain of the LNA. And when you do that, you need to be able to compensate for that by having the same scaling operation in your power spectrum density averaging component of it. So once you have the power spectrum density that's averaged over several iterations to average out the noise, to be able to sense like negative SNR, then you could go into different sensors over here. Like this is a digital TV sensor, which will try to detect at 310 kilohertz tone, and you have an analog sensor over here, which will try to detect at 1.25 megahertz tone. And this is a wireless microphone sensor, which I haven't talked about yet, but just to simplify it, there's two types of wireless microphones, right? There's analog wireless microphones and digital wireless microphones. For digital wireless microphones, it's not an issue because they transmit on the ISM band, so they're out of the picture. But for analog wireless microphones, they actually transmit on the TV bands themselves. So you have to be able to sense them as well. And unfortunately, their output, the transmit frequency, and as well as they're supposed to be like FM modulated signals. Their FM modulation frequency is not standardized. So as it turns out, actually, this is actually the most complicated unit, and there's actually a lot of research into how to build one of these. Okay, so this is the proposed frequency plan by the FCC for TV white space usage. So instead of having the entire analog spectrum, free analog spectrum for any kind of TVWS device, you have the VHF frequencies down here listed in blue for fixed position only TVWS devices. Whereas the green ones are for portable or fixed TVWS devices. The reason for this is that, as I said earlier, as your transmission frequencies go down, as your carrier frequency goes down, your antenna becomes larger, and then it becomes very difficult to implement a large antenna on a portable device. So the way that FCC mandated this is that for frequencies that are within the VHF range, even the lower VHF range, would have to be fixed devices, whereas the devices that operate at higher VHF ranges can be portable devices. So now that we've gone over the concept of signal detection and spectrum sensing and the 82. Just particularly the 82.22 standard, we're going to go into an example of a transceiver implementation of a TVWS device. And in order to do that, we have to understand what the regulatory constraints are, our requirements. Then I'll go over to the wideband transceivers. said right now. We'll just go over the spectral masks, the EIRP, the sense requirements. Then I'll go into just talk about some of the design challenges of RFIC and for TVWS devices. So this is how a spectrum mask looks like. It's defined actually for a TVWS fixed device. So there's two different spectral masks. One's for fixed devices, another one is for portable devices. So for fixed devices, it's more stringent. So what this says basically is that your signal here is within plus minus 3 megahertz, so it's within a 6 megahertz bandwidth. Any output that comes out of the power amplifier has to be that's not within your bandwidth. Has to be for the adjacent channel has to be 55 dB lower, which basically defines the type of output linearity that we need for your transmit path. And this is for the N+1 channel, and for the N+2 channel it becomes more stringent, it's minus 69. And over here, this is actually a very interesting channel, which is the radio astronomy channel. It requires very low, it requires a very clean channel, so it becomes very stringent at that specific channel. And this is for fixed TVWS devices. Now, if you go to portable TVWS devices, it's a bit more relaxed. The reason why it's a bit more relaxed, as we'll see later, is that the transmit power out of the portable device is actually much lower than that of fixed devices. So for the N+1 it's still minus 55, but the N+2 is more relaxed, and for the radio astronomy frequency channel over here, channel 37, is actually more relaxed as well. Now the question, just to give you an appreciation of how stringent these specs are, even for portable applications. I'm comparing here to Wi-Fi 802.11. This is the 5 megahertz version. And as you can see over here, the spectrum mask of the 802.11 is actually much looser than that of that's what's required for TVWS. And this is mainly just to be able to coexist with TV channels that are out there. So now we'll talk about the output power. The spec that's usually given, which is the EIRP, which is the effective isotropic radiated power. It's basically the output power as measured at the output of the antenna. So it takes the antenna gain into effect. So for fixed devices, you usually have plus 6 dB of antenna gain. So your power amplifier actually can be reduced in power. Whereas in portable devices, you actually have negative gain on a dB scale. So the output power on a portable device is actually more. So here, as I said earlier, there's 802.32 standard distinguishes 3 types of devices: a fixed device, a portable mode device, a sense-only device. So fixed and portable mode devices rely on that external database that defines what channels you can use depending on your geographical location. Whereas sense-only devices actually that does not require that database and can actually sense the spectrum itself. So sensing is not required for these first two devices, whereas sensing is required for this last device. As far as output power is concerned, for the fixed devices plus 36 dBm, portable devices plus 20 dBm, the sense only is actually a little bit less as well. And to be able to exist with other TV channels, when it's transmitting at high power, just be on the safe side, the 802.22 standard does not allow adjacent channels to transmit on adjacent channels to actual TV signals. So you'd have to not only make sure that the channel that you're transmitting on, there's no TV signal there, but also the adjacent channels have no TV signals as well. Okay, what about the receive side? So this is all on the transmit side. So what about the receive side? So there's also signal sense requirements, and they've been modified actually in 2010. And these are the new levels, which actually were relaxed in 2010. So for a TV signal, we have to be able to sense minus a 114 dBm signal, and this is measured over a 6 megahertz bandwidth. And if you assume a 6 dB of noise figure in your receiver, if you do your calculations, you'll see that the SNR, you try to detect a signal that has an SNR of negative 14 dB. Okay. This is assuming 0 dB gain your antenna. So if you have lost your antenna, that means you need to be able to sense even a smaller signal. So it's the same value for an ATSC or an NTSC signal, minus 114 dBm. Wireless microphones in 2010 has been relaxed down to minus 107 dBm. And the SNR there is actually positive, so it's a bit easier to sense wireless microphone signals because they transmit on a much lower band. So putting all this together, what I try to do over here is basically just give you an example of what kind of specifications that you have to target for both the transmitter and receiver to have a portable TVWS enabled device. Okay. So portable devices, they transmit on the higher UHF ranges, so 500 to 700 megahertz. The noise rate has to be less than 6 dB. The gain range is from minus 30 to plus 70. This is to get like a 1 volt RMS signal at the output of your transceiver, or receiver rather. And the IP3 requirement is minus 5 dBm. And there's also harmonic rejection requirements. The reason why we need harmonic rejection is that, as we all know, that LO signals these days, especially at UHF frequencies, they're pretty much square waves. So square waves, they have generate harmonics. If you look at the spectrum or an FFT of a square wave, it basically has a fundamental at your carrier frequency, but you also have third harmonic, fifth harmonic, seventh harmonic, and so on, which are fairly strong as well. So these other harmonics, what they can do is they can down convert a blocker in, say, in the cellular band or blocker and Wi-Fi band onto your receiver. So you need some sort of harmonic rejection built into your receiver as well. On the transmit side, again, we're transmitting on the higher UHF range, so it's 500 to 700 megahertz. The output IP3 has greater than 50.5 dBm. This is assuming 3 dB loss in the antenna. So if you have less loss in the antenna, you can actually lower the output IP3 requirements. The output power range is from minus 10 to plus 20 dBm in 0.5 dB steps. If you look at the 802.22 standard, it specifies actually 1 dB steps. But to have some margin in your system, you try to design for 0.5 dB steps. And then you have to have some sort of TX to RX isolation. Just looking at the power levels on your output, you'd want to make sure that they're low enough when you go to the receiver side to be able to avoid the transmitter from corrupting the received signal. So just putting it all together again, this is basically an example of how the receiver would look like. So the receiver would have two channels. Basically, the hardware would be duplicated. You'd have a receiver that would consist of an LNA, programmable gain LNA, a tracking filter that provides some sort of harmonic rejection for you, and then you'd have an RF VGA that provides gain control. Then you downmix, and you want to build some sort of harmonic rejection in your downmixers as well. Then you have IF low-pass filters, as well as programmable gain amplifiers again. And the important point over here is that the LOs here are different. So, and if you make them different, then you can support something like frequency hopping, for example, or non-blocking sensing techniques. And this is an example of an LNA. That's how you could program it, have an LNA that have wideband and programmable gain. You basically make your feedback resistor programmable and DJ resistors also programmable. Wideband transmitter. These days, back in the old days, you'd have something called direct up conversion transmitter. But these days, a lot of people are merging the mixer with the D to A converter. So you'd have a digital baseband signal, would be interpolated over here and filtered out, low-pass filtered in the digital domain. Then you'd go on to something called RF DAC. Okay. And the number of bits required in the RF DAC to meet the 55 dBc adjacent channel requirement, it has been more than 10 bits. So comparing this to, how would this look like compared to a direct up conversion mixer? Here you'd have your direct up conversion mixer. You'd have like a DAC, followed by a low-pass filter, an anti-alias filter, followed by a mixer, and you basically have an IQ mixers over here. Then you add the output of the mixers in the RF domain, and then you might again like have a bandpass filter to clean the signal up a bit more. Then you send that out to the antenna, or power amplifier than the antenna. An RF DAC, what you try to do with an RF DAC is actually combine the DAC operation along with the mixing operation into one block over here. And when you do that, you get this inherent sync function, because you have a sampling operation, so you get a sync function, and the sync function lands at your sampling frequency, so you get inherent filtering there. In addition to this inherent filtering, you want to have some sort of RF bandpass filter over here to filter out the signal a bit more, filter out the alias terms a bit more. Okay. So now I'll go into towards the end. Towards the end. So I'll go over some recent deployments of TVWS. So these are actual commercial deployments that have been implemented very recently here in the US, and as well as there's been deployments in the UK, in South Africa, and Singapore, and actually there's a very interesting study done in Latin America on the 700 megahertz band. So the first deployment actually in the US was in February 2012. It was an FCC approved. It was the first FCC approved TVWS radio system. It was actually in North Carolina, and what they've implemented there is basically wireless video cameras, remote sensors for public utilities are now all have wireless access basically. And there's plans to provide public wireless access in public parks as well. So all public parks within the region would now have wireless access.
You know what frequency they use and what kind of spectrum?
Well, for this I'm not sure. No. And in Singapore, actually very recently, September 2012, there's been an effort initiated by the Singapore Whitespace Pilot Group, which is basically Microsoft, StarHub, and some other organizations that started the first commercial pilot of a TVWS system. This relied on the 700 megahertz band. There's been a lot of discussion for the 700 megahertz band to try to use it either for LTE or a TVWS. So in Singapore, they've actually have like a pilot program to try to implement a TVWS system, and they try to market that as a super Wi-Fi system. So the interesting about Singapore, there's a lot of islands that are off the coast of Singapore that do not have Wi-Fi access. So they try to cover those areas. They consider that as a rural area, so they try to cover that area by providing them with wireless access through the 700 megahertz band. And the interesting thing is that Singapore is such a small country, so these islands out there actually, like the neighbor country is Malaysia. So as it turns out, in Malaysia there's still TV transmission at the 700 megahertz band. So there's a lot of interference there that they have to deal with. And the range of the cell is 5 kilometers, and it's really dictated by the 700 megahertz frequency. So the lower frequency you go, the wider range you get. And that's really the trade-off that you have there. Also, recent deployment in South Africa, and very recent, like in December 2012, they have 10 channels that are available for 2 megabit per second internet access for schools over 10 kilometers of distance. So they basically cover schools within a 10-kilometer radius with like a super Wi-Fi network, but its data rate isn't that high. It's only 2 megabits per second. And the thing that I should note about this, as well as the deployment in Singapore, these are not 802.22 deployments. These are TVWS deployments, but they're not necessarily 802.22 deployments. And actually, this is a very interesting study that was done in Colombia, in Latin America, that compares 700 megahertz bands for LTE or TVWS, like head-to-head, basically. So here this chart shows like a general basic comparison between TVWS and LTE. And if you look at the range over here, down here basically, the range is for LTE is somewhere between 0.3 to 5 kilometers, whereas for TVWS it could go up, it's 33 kilometers, but it could go up to 100 kilometers. But this is really just for a general frequency range of 54 megahertz to 862 megahertz. But once you restrict it down to 700 megahertz, restrict both of them down to 700 megahertz, they both have roughly the same range. And over here, like the maximum data rate, it's basically for uplink and downlink on LTE. It seems to be much more impressive than it is in TVWS. But the thing about TVWS, there's a concept of channel bonding, where you can actually take several channels together and get higher data rates there. So the net of this basically is that they found that the performance of the two was actually comparable. TVWS had a slight advantage in that it had basically adaptive rates and made it more robust under extreme conditions. Sure.
It says 33 kilometers, but that 33 kilometers using megabit, whereas the LTE is 5 kilometers at 100 megabit. You just have to.
Oh, sure, yeah. The main difference here is that if you look at LTE, it's covered basically it's using a 20 megahertz channel, right? Whereas in TVWS over here, the channel bandwidth is limited from 6 to 8 megahertz. So the channel bands are much different as well. But the thing about the TVWS is that there's a concept of channel bonding, where you can take several channels together to meet the performance of this or even exceed the performance of this.
So that's why it's 5 kilometers and 20 megahertz, 33 kilometers and 8 megahertz.
Yeah. And of course, the thing about the distinguishing feature of TWS, it has basically it has a cognitive approach to self-coexistence, which means that you can share a spectrum with others, whereas in LTE there's no such concept. It's basically dedicated spectrum and that's it. So there's other standards other than 82.22. The one interesting standard is actually the 82.11. There's actually an amendment or like a new flavor of 82.11, which is 82.11AF, which defines a PHY and MAC for Wi-Fi operation in the TVWS frequencies. There's also European efforts to define the PHY and MAC, which is ECMA 392. And there's also an amendment to the Zigbee standards, which is 82.15M, to try to support TVWS. So instead of being completely replaced by TVWS, they're trying to amend their standards to try to work to coexist with the TVWS standards. And of course, there's a different standards in Singapore. And one interesting point over here is that this is rumored really that the 3GPP is looking into sharing LTE spectrum with TVWS enabled devices. If this is true, then this is actually a very, very interesting development in that now you can have actually cognitive radios that are built that actually operate at cellular frequencies. So basically, a cellular handset would be like basically a cognitive device as well. Which is really like I guess the natural evolution since the frequency spectrum is so congested that people have to start looking into this. So I think here just one more slide, I guess. These are just some of the players in this space. So as I alluded to earlier, Google's actually looking very actively in the TVWS arena. One thing about Google is that they're a bit frustrated with the progress of 82.22 developing as a standard, adoption as a standard. So they're looking at other competitors, which is 82.11AF standard, to try to promote that. Microsoft actually it's also very heavily invested in TVWS. And Qualcomm actually, there's a lot of research being done in Qualcomm to try to, basically come up with TVWS enabled devices, spectrum sensing techniques, and so on. And there's one interesting UK-based company, startup company, that claim that they already have TVWS enabled devices for different applications. So they have very low power applications, very low power TVWS devices that have battery lifetimes that could be up to 15 years. And these would basically be used for like metering applications. And they also have other devices that are intended for more higher bandwidth applications, such as video surveillance or like a super Wi-Fi type of network. And of course, this is just actually a very small list. There's much more companies actually involved in this right now. So, any questions?
Is this a license
us right now, it's considered to be like the TV spectrum right now is considered to be licensed, but the way that it works is that the feed of spectrum from the analog TV right now, it's basically it was intended to be for digital TV transmission. As soon as analog TV transmission stopped, it was intended to be for digital TV transmission. But a lot of people from the data-centric community, they argued that there's not a lot of spectrum. You guys are just wasting spectrum, basically. There's not a lot of people that actually look at that receive this digital TV transmission, and they'd like to be able to use it for other applications, which is basically data transmission.
Yeah, I was talking about the TVWS. I always thought it was non-licensed.
The TVWS, it's supposed to be like the spectrum itself is supposed to be dedicated for TV transmission. Yeah. But the actual like to be able to transmit on it, you can transmit on it as long as you do not interfere with the TV signals.
So it's unlicensed.
Yeah.
Even the fancy setups that you showed, where they were reflecting at a big base station, and reflecting data, like
That all has to be like with as long as it does not interfere with the actual TV reception. Then
they also have no protection from interference from somebody else trying to use it in an unlicensed manner.
yeah, and that's actually
like Wi-Fi is unlicensed.
exactly, and that's actually one of the main issues in TVWS. Is like okay, they've defined it like how to detect an analog TV signal, digital TV signal to be able to not interfere with those. But then you can have again other unlicensed equipment out there, like social Wi-Fi, for example, can transmit it at their data rate, at their frequencies and everything. But those, as I showed earlier, like if you go back these slides, for example, there's a harmonic projection requirement. So you have Wi-Fi being transmitted at 2.4 gigahertz, for example. So if there's any transmission there, and you're trying to receive a signal that's 1/3 of that.
That's the personal problem for the TVDF.
Yeah.
Right. So I was suggesting, though, if it's an unlicensed service and somebody sets up this big base station, they're collecting, electric power metering or water metering from around the community.
Yeah.
There's nothing there where they're licensed to keep other people from using the same frequencies or channels.
Then
As long as they're not interfering with TV, if they're interfering with this other service.
exactly, and there's a lot of complexity involved in that. It's like how do you ensure that you can guarantee like service operation while coexisting not only with coexistence with TV is important. That's defined by ASL 22 because you can't interfere with that. But then when you actually implement it, you have to coexist with other other places out there. So.
Yes. So I don't understand how the cognitive radio signal sensing techniques could robustly prevent you interfering with television. I mean, the classic kind of hidden terminal problem. You've got 4 locations, A, B, C, and D.
Sure.
A is the broadcast station.
Sure.
B is the TV household. C is one of these unlicensed devices.
Sure.
The TV household at B can hear the TV station, but the unlicensed device in C, which is further away, can't.
Okay.
So when he goes on the air, it's going to interfere with the TV household.
Right. The frequencies, the way the base station determines the frequency that you can transmit on, it depends on the geolocation or the geoposition of your device itself, the TVWS device itself. So once the base station is like, what the TVWS device would have to do is transmit its location, basically effectively transmit its location either through a GPS device or whatnot. And depending on its physical location, the base station will have a database of frequencies that it can transmit on and different power loads you can transmit on over there. And then by that database, you can kind of guarantee that you don't interfere with other TV signals. That's one way, and that's kind of like the simplest way. The fancier approach is that you have like a sensing device on the TVWS device itself that transmits for a certain time, then stops transmitting, then listens around to make sure that nobody started transmitting, then transmits again, and does that periodically.
Yeah, I guess I still don't get it. I understand if you have a GPS database
Sure.
and you know that you can't operate there,
Sure, yeah.
but you can't hear the devices interfering with the household location B cannot hear the TV stations far away. So there's no way it can intelligently
far away, that means it doesn't interfere with the TV signal, right? If I understood you correctly.
I'm sorry, maybe we talked about this separately. But this is, I think, the literature called the internal approach.
Sure.
4 locations. A TV station way over here.
Sure.
B, a listener here. C, a complement radio device.
Sure.
The complement radio device can't hear the TV station, it's too far away.
Sure.
But the listener is halfway in between. He can be interfered with by the complement device, and it'll destroy the TV signals. I don't see how broadcast and unicast can survive unless they've actually got databases for input, because this guy can't hear the TV signal, and yet it's still going to interfere with the user in the middle.
For in terms of the database approach, yeah, I mean that pretty much kind of settles it. Like there's like a table to look up, and that's it. But in terms of like the to have like a basically like a sensing device on your handset, all that it can do really is just sense from your own location, sense whether there's anything there. But beyond that, you can't do anything.
So it really, I guess there's a question as to why they should allow it.
That's why, like for example, in the UK, like in the UK, for example, like they said, okay, you know what, the technology for the sensing equipment is not there yet, so they didn't even bother standardizing that. They said, okay, we're just going to support like database-enabled devices.
I mean, on the other hand, you can say broadcasting is such a dying thing that, so why you just don't regulate it out of existence?
Yeah, for that, it's more of like I guess, you see, you have all these TV broadcasters that like to hold on to the spectrum because it's very valuable spectrum, so it's hard to, tell them, to let go of it. Any other questions?
I just had a quick question, just sort of on the use of the spectrum. You got a few different things, you got Zigbee, the RAN network, LTE. Can you just sort of comment more about that? I mean, we had a good paper yesterday where the speaker indicated that LTE kind of sort of went out because there's billions of mobile phones versus this, like you said, 802.22 is the big fight, it's really slow evolving. Can you just sort of comment on
Sure.
that?
Yeah, that's actually a very good question. Like when 82.22 came out, which came out recently, there's a lot of activity in there. People are really excited about the 82.22 as a standard. But I think whether survives or not, it's difficult to answer. But I think one distinguishing feature of 82.22, which is the cognitive radio approach, where you actually can coexist with other channels, that I think that feature would move on to whatever feature network we come up with, whether it's 82.22 or some other standard. I really think that feature is there to stay for a while.
But as you said, that really hasn't improved because not being able to detect interference is absolutely killer for those few households that are between 2 weak signal places where both different transmitters are happening.
Yeah, sure. That's for the case where you have like a sensing operation on the handset. So, but what I see is that like for in the future, like you'd have to have some sort of database approach. That's always going to have to be there. Maybe the sensing operation can augment the performance of your devices. So.
I think another thing that comes in there is Stu's question was the power levels of these devices we're talking about are dwarfed in comparison to the transmitter broadcast field.
Sure.
So I'm not sure you can get a situation like you're describing it correctly. You can get one where your device that's trying to sense it is trying to build, and you have a line of sight to the other guy and line of sight to the other guy. I think that's where the database system comes in, right? They can even register wireless microphone systems.
You can try to register everything.
Yeah.
That could work.
Yeah. But it's kind of like too late to worry about whether it's going to come.
I mean, yeah, the database approach is like a fail-safe approach as long as you can register everybody. But I think the thing about microphones, so like you can register microphones, but there's no guarantee that somebody's going to buy some equipment out there and just start using it, right? But yeah, I mean that's really the fail-safe approach, just to have a database to cover everything. question?